Physics 201, Critical Thinking Task 80. This problem is due Tuesday night at midnight. I'm going to give you some hints here. This problem is asking you to rank these boxes by their final momentum. I'll give you some background here. Well, some additional questions to think about in regards to this problem and some strong hints. You could easily figure out the impulse here on these boxes, which would be the change in momentum. So it would be easy to rank these by change in momentum. For example, it says in each case, this is the net force applied. It already incorporates friction. For example, there might be an applied force of say 120 newtons here and a frictional force which is not showing up 20 newtons. Therefore, the net force to the right is 100 newtons. So that's all we got to worry about right now is that's the net force. And there might not be any friction, so there might be just that applied force of 100 newtons. There's also, if you're drawing a free body diagram, a force of 100 newtons down for the weight and the normal force of 100 newtons up from the floor. But we don't need to worry about that in this problem. That'll be an F net of 0. But to the right, the box will accelerate, its momentum will change, given this net force. But once again, impulse is your average or net force times your time of application. It says it's 10 seconds in each of the 6 scenarios here. So the impulse in A is the force, 100 times 10. The impulse is 100 newton seconds. Well, it's going to be the same impulse in F. 100 times 10 is 100, or 1,000. Did I say 1,000 for part A? It should be 1,000. And for F, it's 1,000 newton seconds of impulse. That is how much the momentum changes by. That's the change in momentum. So A and F would be in first place if you were ranking these by change in momentum. And then C and E would be in second place for change in momentum because the change in momentum, impulse for C and E, are both 75 times 10, 75 newtons times 10 seconds, 750 units of impulse, which is causing that much change in momentum. And then B and D would be in last place, ranked by change in momentum or impulse. But you have to rank these by final momentum. So without finishing off the problem for you, what you have to do in this problem is actually figure out what momentum they start with. For example, A, all of these boxes start, they're moving already when the problem is initiated. They're all moving to the right at 10 meters per second. And so, for example, box A it's starting before the application of the net force. It's starting with a momentum of 100 units, 100 kilograms meters per second of momentum to the right. And it changes this momentum already by what we said in previous, the impulse was 1,000. So its final momentum is going to be 1,100 units, 1,100 newton seconds, which is equivalent to 1,100 kilograms meters per second to the right. So keep that in mind if you're going to rank these by final momentum. I've given you a lot of hints there, so you can finish that one off for tonight. That's due at midnight. Critical Thinking Question 53, Tugboat Force. This is a good exam review question. Really dealing, and there's a bunch of sub questions I could ask, but let me just go directly to the problem at hand here. You have a tugboat on the left pushing on 2 barges. Barge number 1 is in the middle and barge number 2 is ahead of it. And everything is being pushed to the right and gives you all the masses of the tugboat, the masses of the barges, the current acceleration, and they're all accelerating to the right. There's different masses. So I could let me give you a sub-question. In A, I could ask you, what is the acceleration of that system? And it says ignoring all frictional resistive forces. And that would just be an F net equals ma towards the right. Well, it tells you the acceleration. What would be the net force that causes this acceleration that the tugboat has to push on barge A with, barge number 1? And the net force would be equal to the total mass that it's pushing. All right, so then the total mass, to add up these two masses, would be 2,000 plus 1,000 would be 4,000 equals that times 1.2 would give you the force that's being applied to barge 1. You would not include the mass of the tugboat in that calculation. But that would give you the net force, the pushing force on barge 1. And you could do that in all 6 cases. The thing here that's really kind of tricky, it says in the problem, calculate the force the tugboat exerts on the lead barge. That's barge number 2. And the answer is 0. It's not pushing on barge 2. So that would be the answer to this problem. The force that the tugboat exerts on barge 2 is 0. it's barge 1 that's exerting a force on barge 2. All right? So you could figure out the force that the tugboat is exerting on barge 1. Once again, you just turn or add up the two masses and then multiply by the acceleration. And you could rank these by the force exerted on barge 1. Then you could also figure out the force that barge 1 exerts on barge 2. You could actually do that as before anything else as well. For example, all you have to do is figure out, well, mass of barge 2 is 2,500. And it's accelerating at 1.2. So all you got to do is multiply those two numbers, 2,500, proper units, that's good, times 1.2 would give you the force necessary on barge 2 to make it accelerate at that rate. So that would be the net force if there's no friction, because we don't need to worry about up and down forces. Those cancel here. All we need to worry about is the force, the net force in the direction of the acceleration. So that's how you could calculate the net force on each barge. But it's only barge 2 being pushed by barge 1. And by the way, whatever force barge 1 is exerting on barge 2, Newton's third law says that barge 2 is pushing back on barge 1. So that would be a bunch of sub-questions you could be asked for that particular situation. Critical thinking question 77, another good Unit 8 question, momentum and impulse. Once again, when you hear the term or phrase change in momentum, equate that to impulse. Impulse is average force times time. Anyway, this one is asking us to rank the change in momentum for these carts. Now, there's 6 scenarios here. In situation A, we have to rank these by the greatest change in momentum from greatest to least, positives to the right. So I'm going to rank these because the negatives are a little tricky here. They want negatives. The bigger the negative is, the smaller number. But I'm just going to do these by magnitude. Let's just do this by magnitude. I don't want to mess around too much with negatives here. Although we got to pay attention to it a little bit. Let me explain. For example, what's the change in momentum of A? Well, it's really not that hard to figure out. You figure out the momentum at the beginning is 4 times 10 is 40 units of momentum to the right. And at the end, it comes to a stop. It hits this barrier and comes to a dead stop. So it starts off with 40 units of momentum and ends with 0. So its change is negative 40. That's its change in momentum. We're just going to look at the magnitude there. All right. Let's say it's 40 units. It lost 40 units of momentum. All right. Let's go B. B is right here. All right. So at B, it starts off with 3 times 10 is 30 to the right. But it bounces off and bounces backwards. So now it has 10 units of momentum to the left. So here's we got to think a little bit. It's not that hard, but these bouncing situations are really, well, you can easily get them wrong if you don't think about the fact that it's changing direction. For example, the original momentum is 30 to the right. The final momentum is 10 to the left. So the change is 40 units to the left, which technically would be negative 40. So it would be tied with A so far. It's a negative 40. So it started with 30 to the right and 10 to the left. So some people would say the change in momentum there is 20 because it was 30 and then it was 10. Well, it was 30 and then negative 10. Change is negative 40. That's also the impulse. And if it told you how much time it was in contact with the wall, you could figure out the force the wall applied because the impulse would be the negative 40 equals that average force times the time it is in contact with the wall. That would be a good variation of this question. Part C. Initial momentum is 25 to the right. Final is negative 15. That's to the left. That's also a change of 40 to the left. Tied again. And if you go through all of these in this case, part D, the initial momentum is 40 to the right. It comes to a dead stop. So its change is 40, negative 40. And in fact, all of these are negative 40. E is 20 to the right to start, and final momentum is negative 40. So its change is negative 40. And F as well. Starts off with 20 to the right, units of momentum, and 20 to the left, change of 40. So they're all a change of negative 40 kilograms meters per second. Same impulse, same change in momentum, so they'd be ranked all with the same change in momentum. Critical thinking question 88. This has a lot of good review in this particular problem. This is an overhead view of a turntable, and let's say they're all rotating, it says they're all rotating with the same angular speed, which is omega. I'll write that down. That's good. Unit 10 also was in Unit 6, I believe. Omega, that symbol right there stands for rotational speed. It could be in RPMs, but we like to convert that to radians per second, which we probably won't have to do here, but we could. They all have the same rotational speed. Actually, it doesn't tell us what it is, so we could pick any number. 1 radian per second if we want to do some calculations, which we might here. So, overhead view. There's these little blocks of different masses sitting on the table. So another question I could ask, review question, as these things spin, what force keeps these blocks on this turntable? Well, it's a centripetal force. That's the general term. And centripetal force, with a P, is mv squared over r. I believe that's in Unit 6. And in this case, though, specifically, the centripetal force is friction. If there's no friction, these blocks do not stay on that turntable. Same is true when you have a car that goes around a corner. Friction is the centripetal force. Other centripetal forces can be gravity. That's what keeps planets in orbit, the centripetal force of gravity. For a ball on a string, the centripetal force is the tension in a string. So centripetal force is a generic term for a center pointing force that causes acceleration toward the center, centripetal acceleration, as you go in a circle. That's a quick review. Now in this problem, we want to rank these by the centripetal force. The horizontal force, that's the only force. And I'll take, well, I'm just going to take C because that's the easiest one. I'll go to C. All right. So there's a force, call it F sub C, towards the center. There's also an acceleration towards the center. That is the only force acting on this block right. Well, no. There's also the gravity towards the floor, which would be hard to draw here because this is the overhead view. It'd be pointing into the page, and the table force, the normal force, would be pointing towards me or towards us right now. Doesn't really matter because those forces will cancel out. No net force up and down. The net force is towards the center, centripetal force. It is the force of friction, and we did problems like this where we found the coefficient of friction for particular cases for cars going around corners. All of those are fair game for the exam. The general equation here for centripetal force is F sub C equals mv squared, that's the tangential velocity, mv squared over r. That's an r right there, not a v. All right, mv squared over r, where v is the tangential velocity. And remember, the tangential velocity, I don't want to draw it on a diagram right now, but the tangential velocity would be like, if these are, this is rotating counterclockwise, the tangential velocity would be straight up in that direction from this spot towards the top of the page. You point an arrow that way for the direction of the tangential velocity at this point in time. Now, one thing that's very important in this problem is connecting tangential velocity to rotational speed, omega. If you go back to that unit, or unit 10 or 6, the tangential velocity, v sub t, equals r times omega. So I'm going to plug that in down here for this particular situation. The centripetal force is m times r omega squared over r. Now if you simplify that, you get the centripetal force, which is the force of friction once again, equals, well, what's going to happen mathematically is you're going to get m, and you get r squared, omega squared. But one of the r's will cancel out, so you just get mr omega squared. That's important here. I'll circle that. And you could set that equal to the force of friction if you had to actually calculate the force of friction. Force of friction would be mu times r sub n. We did that in the car problem. So you can go back and look at that. But here we don't need to figure out the actual force of friction, even though it is the centripetal force. We got to rank these by the size of this force. But now we have enough information we can just plug in. And here's the thing. In each case, we know m and we know r. So in this equation I just wrote down, I know m, I know r. I don't know omega. But what I do know is that in all 6 cases, it tells me in the problem that omega is the same value for all problems. So it will not affect the rankings. So omega could be 1, 2, 3, whatever it is. But in all cases, it's the same, a 1 radian per second. Doesn't change. But what does change in each case is m and r. So really all you have to do here in this case is rank them. You could actually calculate these. Let's say let omega equal 1. I'll just let omega equal 1 radian per second. So for example, in situation A, the force equals, it's the mass, which is 6, times r, which is 0.02, times 1 squared. So the force, the centripetal force, the force acting on it, is 6 times 0.02, which would be what? 0.12, and it'd be newtons, towards the center. Bottom line, all you end up doing is multiplying the mass times the radius to get the centripetal force. And if you look at all these then, all right, I'm not going to do them all for you right now, but we can kind of do them in our head. For example, in part B, the frictional centripetal force would be 3 times, basically 4 times 0.03 would be 0.12 as well. So that would give me the same answer as A. And just in generic terms, I'm just going to make it a little easier on myself. Let's say the answer to A was 12. The answer to B would be 12, 0.12. C would be 5. D would be 10, 0.10. E would be 6, okay, 0.06. And F would be 15, 0.15. So the ranking would be F in first place with 0.15 newtons. And then, what do we say? A and B with 0.12 newtons. And then D with 0.10 newtons. And then E with 0.06. And then C 0.05 would be the last place. So that would be the ranking based on the horizontal force, which would be centripetal force, force of static friction. Critical thinking question 8-9 or 89. And this is a good Unit 10 review question about moment of inertia, or what I like to call rotational inertia. There's 6 different figurines here. There's like 3 sticks with little weights on the ends. I don't know if you've ever played this game, but if you ask your parents or grandparents, they used to play a game that's called Jacks, J-A-C-K-S. You'd have a whole bunch of little things, but they're 3-dimensional, but they're like the size of a quarter, but 3-dimensional. And you would have like 12 of them. You'd throw them on the floor, and they'd kind of spread out, and you had like a rubber ball. You can look this up. Game of Jacks, J-A-C-K-S. Maybe you've played it. You throw the ball up, you let it bounce, and then you grab as many jacks as you can, and then catch the ball before it falls. And then you get to score that many points. It's kind of a fun game. Once again, this is old school. It's an old school game. Your grandparents, I'm sure, played it, or your parents. Jacks. And we used to spin these things like tops. But bottom line, they're 3-dimensional. In this case, there's 3 massless sticks, axes, X, Y, Z axes, all perpendicular, and they have weights on the end. In this case, what they're saying is the little weights on the end are point masses. They basically have very little size because we want to concentrate on the moment of inertia, rotational inertia. But there's some brass ones and some aluminum ones. The brass ones are shaded. So the aluminum ones are not shaded. And the brass ones are heavier, or more mass. Let's say they're twice the mass. Doesn't really matter. But they're more massive than the aluminum ones. We'll just do this one conceptually. But bottom line is, it's going to say, okay, try to spin these things about the z-axis. I'll kind of highlight that on A. So if I have an axis, this line right here, and if I were, I don't know what happened there. Let me erase that. But if I draw that line, okay, I'm going to spin that like a top around that axis. So there's only going to be 4 of those weights, the ones on the X and Y axis, that are actually going to be spinning. The ones on the Z axis won't be spinning. So they will have 0 rotational inertia with respect to that axis. So if you're on the axis and you're a point mass, you have no rotational inertia, 0. So we don't count the 2 that are on the Z axis here. So bottom line is you'll have 4 point masses, and the moment of inertia for a point mass, is just mr squared. And in case A, there's 4 aluminum masses, and we'll say each of them has a mass of 1 at a radius. All the radii are the same here. Let's say the radius is 1, the mass is 1, so each little mass will have a moment of inertia of 1 times 1 squared is 1, but there's 4 of them in part A. So in part A, the total, the sum of all four of them in part A, all four of the little balls, would be 4 units of inertia, rotational inertia. And the units are, you really don't need the units in this problem, kilograms meter squared. But it'd be 4 of them. All right? I just made up a mass of 1 and a radius of 1, so each one would have 1 unit of total inertia. In part B, all right, same axis, but in part B, the sum of the inertias in part B. Now, in part B, there's 2 aluminums. Each one of them is 1 mr squared, 1 m, 1 r. But then let's say the aluminum ones, or the brass ones, there's 2 of those. They each have a mass of 2. So, actually, I'll write it all out here. It'd be, for each aluminum one, it's going to be 1. So it's going to be 1 plus 1. And the units are kilograms meters per second. In case A, it would have been 1 plus 1 plus 1 plus 1 equals 4. But in this case, there's 2 spheres that each have a mass of 2. So for each brass mass, it's 2 times 1 squared. So it's a 2. So each brass object will be 2 plus 2. So for the total in B, the total sum of all the inertias is 6 kilograms meters squared. That's what the total will be in B. Well, if you try to spin about that z-axis, because they're rotating, there's 4 balls only that are 4 spheres that spin about that axis. In part C, it's the same answer as B, because there's two brass spheres and 2 aluminum. So the answer for C is the same as B. The answer for D is the same as A, because there's just 4 aluminum spheres circling around or spinning around axis Z. E and F are going to be equivalent, but in E and F, sum of the inertia in E and F, spinning about that axis, up and down axis, there's 4 brass spheres, so it's going to be 2 plus 2 plus 2 plus 2. So the total there for E and F, the sum of the total moments of inertia is going to be 2, 4, 6, 8 units. Oops, that's kilograms, not meters per second. Kilograms meter squared, not per meter squared. So the ranking would be, the hardest of these to spin, to rotate, would be E and F, tied for first place. They have the greatest inertia. It's hard to get them spinning, but once they're spinning, they will have more momentum and more tendency to keep spinning. So E and F, first place, 8 units. And then tied for 3rd and 4th place would be what? B and C with 6 units. And in last place, the easiest to spin, the least amount of rotational inertia, A and D. All right, that's a good summary for moment of inertia, rotational inertia. The difficulty with which it is to spin something, it's at rest, it does not want to start spinning. According to Newton's first law of motion, for same things in linear motion, they don't want to keep going in a straight line. These things don't want to be spun. So you can apply Newton's 3 laws of motion to rotation, especially the first law. And the second one, torque net equals ma, we'll do that on the next problem here, or certainly in the homework. Critical thinking question number 90. Angular acceleration for some thin horizontal rods, or thin rods. This is a top view, and this circle in each diagram is a pivot point, so this rod, kind of like the hands of a clock, can spin around that spot. And it has something to do with torque. Well, it's an application of Newton's second law for rotational systems, and that is torque net, that's that tau or T, equals I alpha. Torque net equals I alpha. And we're looking for the angular acceleration here, alpha. And we have to talk about and come back to the moment of inertia. We did that for those jack problems in the previous critical thinking situation. But here we have a thin rod that's uniform mass and has a varying length in this case. If you look this up in those tables in Unit 10 or online, for a thin rod is very important. Thin rod, the moment of inertia about its end point, the value for I is 1/3 mr squared. You always have that mr squared, but this is 1/3. If you try to spin a rod about its middle, a thin rod about its middle, I think it's 1/12 mr squared. It's much easier to spin it. It has way less rotational inertia, way less moment of inertia if it's spun around its middle. But this is being spun or trying to rotate around its endpoint. It's 1/3 mr squared. So we're going to need to know that. I'm going to actually plug that into my tau net. I'm going to take this and plug it in there. And actually, I'm going to take my tau net equation and solve it for alpha first. So I'm going to bring this equation down. So I have alpha equals the net torque divided by I. It's going to be important in this problem. Okay, and torque is force times distance times the sine of the angle. So I'm doing a lot of review here. Torque was in unit 9. It's force times distance times the sine of the angle, theta. The nice thing is you'll maybe notice already in this problem, well, let me plug everything in, over 1/3, that's 1/3 mr squared. All right, where r, actually, I could have put there that r is the length of the rod. I'm going to change that. R is the length of the rod, 1/2 ml squared. I mean r, it's a length. R is a length. So 1/2 ml squared. That's how it usually will be printed in the literature. But going back to torque is force times distance times the sine of the angle. In all these cases, the angle is 90 degrees. It's a cross product. Remember, with work problems, it's a dot product. It's cosine of the angle. For torque, it's the sine. It's the cross product. Work was dot product. Torque is cross product. Sine of the angle. The angle is 90. Sine of 90 is 1, so it won't matter in this problem. While the angle is 90 in all cases, so it'll drop out. So we'll drop out the sine of theta because it's a 1 in all cases in this particular problem. Now, if you rearrange this equation, you get alpha, the angular acceleration, is 3 fd over ml squared, where L is the length of the rod, F is the force applied, M is the mass of the rod, D is the distance at which the force is applied, not necessarily the length of the rod. All right, because if the force is not applied to the end, which it is in all cases except for one here, you got to go with where the force is applied. So I can just do 6 calculations here. I'm going to do a few of them for you. For A, the alpha, the angular acceleration, is going to be, I'm going to use this equation over here. I'm going to circle it. And you're going to find out that the 3 doesn't really matter, but I'm going to use it anyway. But in case A, you have 3 times the applied force, which is 2F, times the distance at which the force is applied, which is 2L, divided by the mass of the rod, which is 2M, times the length of the rod squared, which is 2L quantity squared. So if you do the math here, all right, what's going to happen is, and I'll change a little bit here. The first time through it, I'll go a little slower. This 2, these are all factors, so you can cancel out. That 2 will cancel that 2. Now we have a 2L on the top and a 2L squared on the bottom. So that total 2L will cancel one of those, but we're left with one of the 2L's on the bottom. The end result, when you simplify that, because when you have factors like that, it's fairly simple to simplify it. In the numerator, you end up with just the 3F. And in the denominator, you end up with, the conventional way to put that is 2ml. 2ml. That would be the angular acceleration of that particular rod, if there's no friction in the bearing, which we're assuming. Okay, that's the angular acceleration. All right, so now I just got to do B. I'll do a couple of these. In B, the angular acceleration is once again, 3 times the applied force, which is 4F, times the length of the rod, or the length, the distance from which it's from the reference point. The reference point is that pivot point. That is a distance of 4L in this case, divided by the mass of that rod, it's 4M, times the length of the rod squared. Length of this rod is 4L squared. So once again, if you go through the math, the 4's here cancel. They don't always, in some of these, they're not all going to cancel. But this does cancel one of those. And your final alpha here in this case for this case is, what, 3F, you're always going to have that 3 or a factor of 3 up there, over 4 ml, and that's it. So far, A has got a bigger acceleration than B, so it would be ranked ahead of it. Now I'm gonna fill in some of these. The one that's hardest is D, but let me fill them in and just comment on them. So I did all those similar calculations that I did for A and B. The only one that's unique is D as in Dave down here. Because if you look at the diagram, I mean, the applied force is 2F, but it's applied at the pivot point, not at a distance from the pivot point. So the distance is 0. So it really doesn't matter what the rest of that problem is. It's the angular acceleration is going to be 0. There's no applied force, no applied torque, because the 2F force is applied right here at the pivot point. And in general here, the greatest acceleration is going to be for the shorter sticks because they're easier to rotate. A longer stick is going to be hard to rotate. It's going to have more inertia. And if you have a bigger force, you're going to get more acceleration as well. So those are the two general principles. Bigger the force, the more acceleration you'll get. Bigger than net force. So these are the net forces, the net torques, which we are assuming here because there's no friction. And then the lesser the inertia, the more the acceleration. So to complete the ranking here then, C would be in first place with the biggest because they all have this F over ML. So all you look at is the factor in front, the number in front. So 9 is the biggest number. So if C is in first place, it's a 9. And then what, E, which would be 9 divided by 4 is 2 point something. That'd be second place. Then A would be in third place with a 1.5. And then B would be in fourth place with 0.75 as the factor. Then F, which is whatever 9 over 16 is, which is a smaller number than 0.75. And then last place would be D, no acceleration. And that's the ranking. And finally, critical thinking question 95. This person's holding a stick. They have to apply a counter torque to balance off the torque created by the weight hanging, or the weights hanging. The weights are trying to make the whole system rotate clockwise, so the hand produces a counterclockwise torque. These are in equilibrium. They satisfy the two conditions for equilibrium. First of all, the translational or linear equilibrium. There's no net force up or down, left or right, so there's no linear acceleration, and there's no rotational acceleration. The second condition for equilibrium, holding this thing at rest, static equilibrium. So all we have to do is look at the torque generated by each of the scenarios, and torque, once again, is force times distance times the sine of the angle, and luckily, once again, the angle is 90 degrees in all cases, so we're not going to factor that in. Okay, now, just to be consistent, 500 grams is 0.5 kilograms. That is a weight of 5 newtons. I'm just going to use 1 sig fig. This is 10 newtons. It's 1 kilogram times 9.8 is 10 newtons. This is 7.5 newtons. I'll refer to that. That's the weight. That's the force applied. And then we have 10 newtons here. That's just a good review. 5 newtons. So there's 2 weights, 2 forces applied, trying to make the stick rotate clockwise. This is 10 newtons. And once again, you just take the mass in kilograms times 9.8, rounded off to 10. 5 newtons and 5 newtons. So in case A, I'll try to do it over here. What is the torque generated by the weight? Well, the torque generated by the weight is the force, 5 newtons, times the distance. Now, we don't know how long these meter sticks are. But let's say they're sticks. Let's say they're 1 meter long. So that's at a distance of 1. So the torque in A is 5 Newton meters. That's Nm, 5 Newton meters. That's the torque generated in A. All right. If we say let L equal 1 meter, L equal 1 meter, the length of the rod. Okay, B. All right, the torque in B by the weight, which has to be countered by that offsetting counterclockwise torque with the hand, which is then just the ranking of the difficulty. The more torque the hand has to apply at the same spot, the more difficult it is. That'll be the ranking. So in part B here, it's a 10 Newton force, but the distance is 0.5 meters, half a meter. So the torque in B is, well, 5 Newton meters. Let's go to 1 sig fig. And you keep going here with this, In C, it's going to be the torque of 7.5, a force of 7.5 times the 1 meter. So the torque is 7.5 Newton meters. So that's on first place so far for C. All right, let me pause and do the other ones. Well, the other ones are a little bit more difficult. In part, I'll go down a little bit further. So I did all three of the last ones. In part D, though, there's two clockwise torques. It's the 10 Newton weight at a distance of 0.5 meters, which generates the clockwise torque of 5 Newton meters. And then the weight at the end, the 5 newtons at the 1 meter mark. That's this calculation here. So it's going to be 5 plus 5 is 10. It's interesting that in E, you get the same answer. If you just put the full 10 Newton weight at the very end, you get the same torque. It'd be the same difficulty of holding the stick, because you have to generate the counter torque to that particular torque. And then F, it's 5 newtons force at a distance of 0.5 meters, half the length, which is 2.5, plus 5 times 1 is 5, 7.5. So the ranking would be, first place, D and E, tied for level of difficulty for the person holding the stick. And then C and F tied for third and fourth place, and the last place would be A and B for the level of difficulty to hold the stick in static equilibrium.